Okay, so today I'd like to try and provide motivation for shared sequencing. And the title of this talk is, why is synchrony valuable? If synchrony is not valuable, then we don't need to do shared sequencing. And so I could have titled this talk, why shared sequencing? Now, just so that we're clear, synchrony is a real word. It comes from the Greek. It means like things happening at the same time, synchronos. And in the context of sequencing, it means that the sequencing of transactions over multiple rollups is happening at the same time. So here you have this notion of a super transaction, which is a transaction that touches multiple rollups. So you have the yellow rollup and you have the green rollup, and the super transaction basically all happens in one single block with this shared sequencer. So that's the synchronous model, and then it's in comparison to the asynchronous model, where basically the super transaction happens in multiple steps. So one example could be, I have some ETH in rollup A, the yellow one, and I want to buy an NFT in rollup B. Step one is I send the ETH to rollup B, and then once the ETH has arrived in rollup B, I buy the NFT, and then I send the NFT back to rollup A in the final transaction. So my basically thesis is that this right model here is significantly more complicated and messy than the left model, and I'll try to argue this with specific examples. And one of the things that I've noticed is that there's actually high correlation between success and synchrony. So on the left here you have the two most successful chains, Ethereum L1 and Solana, they're in the synchronous model, and then you have alternative projects like Cosmos that have gone full asynchrony and have created a lot of friction for users and developers. And I think this correlation between synchrony and success is not a coincidence. There's actual correlation going on. Now, I'm going to split the talk in three parts. I'm going to talk about the UX benefits of synchrony, as well as the developer benefits of synchrony. And then I'll talk about some of the counter-arguments that people put forward arguing against synchrony, and I'll try to respond to those. So argument number one is this idea of fee certainty. If everything happens in one slot, in the next slot, I know what the gas price is for the next slot, and I can just pay the exact fees. It's very straightforward. On the other hand, if things are happening in the future, I don't know what the gas price will be in the future, and so I have to basically make more transfers to deal with, cleaning up the change from spending gas. And also from a UX standpoint, there's just less certainty as to how much I'll end up paying for my super transactions. Another very obvious point is latency. So if you have a super transaction that happens in one slot, well, it all happens in the next slot. Whereas if it happens over three different slots with three different sequences, three different proposers, then it just takes more time. So if the slot time is, let's say, 2 seconds, on the left it would take 2 seconds, and on the right it would take 6 seconds. But things get even more extreme when you introduce pre-confirmations. So pre-confirmation is this idea that you have a well-defined next sequencer, and you can ask them to commit to the state of your transactions, and you can get 100 millisecond pre-confirmation times. And so now if you compare the left and the right, you have a 60x difference. The right takes 6 seconds, the left takes 100 milliseconds, so that's almost 2 orders of magnitude in UX latency. Now you could have a pre-confirmation for the very first transaction, but you can't easily get pre-confirmations for the next two transactions because you're dealing with different sequences. Another aspect here is shared liquidity. On the layer 1 and on Solana, for example, we have the notion of an aggregator like 1inch or Matcha. Like the reason why we don't have 1inch for all the rollups is due to asynchrony. And so as a user, what I have to do is I basically have to hit the closest liquidity pool, which is local to my rollup, and that's going to be only a subset of global liquidity, and so I'm going to have to suffer larger spreads and higher slippage and basically get worse execution as a user. Argument number 5 is liquidations. So Aave right now, the way that it's designed is that it assumes that when it needs to liquidate, it can just liquidate immediately. But if you have to do asynchronous liquidations, things start to break down. And so things like Aave actually don't work very well in an asynchronous world. And then 6th argument, I guess, is flash loans. When you're in a synchronous world, when everything happens in a single block, you can open a flash loan at the beginning of your super transaction. Your flash loan can flow through multiple rollups, A, B, and back to A, and then you just pay back your flash loan. In the context of asynchrony, you can't take flash loans. And so if you want to do loan rebalancing, or you want to do some sort of fancy arbitrage, or whatever it is with your flash loans, you can do that in the synchronous world, but you can't do it in the asynchronous world. And this is a bit of a summary slide. Over time, our applications have become more and more complicated. So we started with very simple transfers, and then we had swaps, and then once we have swaps, we can do loans. And in the future, we might have very complicated things like marketplaces. And even for the simple applications, there's benefits to synchrony. But imagine the complex applications. Imagine you have an application that touches 10 different zones, and all these 10 different zones are asynchronous. It becomes extremely messy. And so one of my intuitions is that the value of synchrony grows over time. It's valuable today, as we can see with chains like Ethereum L1 and Solana, but it's going to be even more valuable in the future. Okay, so that's for the UX arguments. What about the DevX arguments? So one of them has to do with reversions. Today, block builders provide reversion protection as a service. So if I submit a bundle to a builder and this builder fails or reverts, then the builder can just remove it from the block. And so only successful bundles go on-chain. And the same thing can happen with a super transaction. I submit a super transaction to a builder, it does all the simulation, and it just works. But in the asynchronous world, we don't know a priori where the reversions might happen. So you start your super transaction on rollup A, and then something might fail in rollup B. So in the NFT example, someone might have bought the NFT just before you. By the time the ETH arrives, someone bought the NFT. Or maybe another example could be that suddenly the gas price on rollup B spikes to infinity, or all the blocks are full, whatever it is. There's lots of congestion, and now you can't even afford the gas price on rollup B. And so what you need to do is you need to deal with these reversions, you need to clean things up. And unfortunately, the process of cleaning up might not be straightforward, because you're going to be, first of all, you're going to be consuming gas to do all the cleaning up. But there's some operations that might be irreversible. And so you have this Frankenstein partially executed super transaction, which you're not happy with. A second argument is around the weakest link. So in the context of having multiple sequences, let's say we have k different sequences for a super transaction, any k of those sequences can fail. So there could be accidental liveness failures that has happened to every single centralized sequencer, to my knowledge. And there could also be censorship opportunities. And so now here you see with the liveness guarantees are falling down to the weakest link. On the other hand, in the shared sequencing model, presumably what will happen is that the community would converge towards an extremely secure shared sequencer, maybe Ethereum itself, like the most secure shared sequencer, and you basically benefit from the strongest link as opposed to the weakest link. Another very nice benefit of shared sequencing is data compression. So it turns out that the more data that you're compressing, the better your compression ratios become. And so ideally, you want all the rollups or as many rollups as possible to share the compression of their data. And this is very easy to do with shared sequencing because you basically have this one entity, the shared sequencer, which can take the data of all the rollups, compress everything in one go, and then submit that into the blobs at layer 1. And this, of course, is very different to the asynchronous world where every rollup is creating its own batches and they get compressed individually. And so you don't have the same compression efficiency. A very similar argument can be said for proof aggregation. Right? We want to be in a position where you only submit, you submit very few proofs on chain, and these are aggregated proofs across multiple rollups. When you have a shared sequencer, you have a very well-defined entity that is incentivized to do this proof aggregation because they receive transaction fees from users and they need to pay for the cost of settlement, and they want to minimize the cost of settlement. But in the context of asynchronous proof generation, you actually don't have these incentives. So you have, let's say, 2 different rollups, each submitting batches with proofs. They submit them in the mempool. The L1 builder, you could say, okay, maybe the L1 builder can do the aggregation for you. But there's an incentive misalignment problem here, which is that the L1 builder is paid with tips. And so you have the rollup A proof, which pays tip, the rollup B proof that pays tip. And so if I do the aggregation, I only receive 1 tip as opposed to getting paid twice the tip. And so in some sense, the L1 builder is incentivized to make the rollups pay as much as possible for settlement, which you don't have with shared sequencing. And then another question around asynchrony is, how are we going to do orchestration? So in the context of a synchronous super transaction, you have a single entity, the block builder, who is sophisticated and can just arrange all the transactions so they all line up perfectly. But in the context of asynchrony, you need some sort of monitoring agent that can do the scheduling on behalf of the user. So for example, a wallet. Now, unfortunately, wallets are extremely unsophisticated if anyone's used MetaMask here. And so we can't hold our breath that MetaMask is going to implement very clever scheduling logic, do this, and then if this reverts, kind of roll back and blah, blah, blah. It's going to be very complicated, in my opinion, to actually implement this at the wallet level. But in the shared sequencer paradigm, it's much more clear which entity should be doing this scheduling and orchestration. Okay, so at this point, you may be thinking, wow, there's so many advantages to synchrony, and it's highly correlated with success. Let's all move to a shared sequencer. But there's counter arguments that people bring forward, and I want to try and give those counter arguments and kind of try and give responses. So one counter argument is that locks don't scale. So if you want to do the really fancy synchronous composability like the flash loans, then you need to take locks across a state on multiple rollups, and those can be quite expensive. And I basically have 2 answers to that. Answer number 1 is that some of the benefits, some subset of the benefits that I talked about don't rely on locks. So if you want the shared compression, the shared proof aggregation, the shared censorship resistance, the shared finality, all of these things, you don't actually need to pay for locks at all. And then the second answer is if you do want the very fancy flash loans across multiple rollups, then you shouldn't be scared of scarcity. In some sense, the whole space thrives on scarcity, and we want to treasure the scarce resource. And the way that we deal with scarce resource in our space, just like scarce block space, is that we have a market. So there's going to be a market for taking locks, and you will pay a premium as a user for the privilege of taking these locks. Counter-argument number 2 is that if you want to do the really fancy synchronous composability like flash loans, you need to have real-time settlement and real-time proving. So the various rollups don't want to trust each other, and so you want to do these real-time withdrawals within the block at the transaction by transaction level. And today, we don't have real-time proving with SNARKs. So what are we going to do? Well, it turns out you can fake it till you make it. And in our space, we're very comfortable faking it, for example, by not having fraud proofs. And so we can do something very similar here. So we can have some sort of multi-sig that will sign off in real time on state transitions. This is very convenient. It could be a one-of-one multi-sig. It could be totally centralized. And the other amazing thing is that secure enclaves like SGX also have real-time proving. And this is in production today with Tyco. They have real-time proving. And so you can even combine the two, right? Like in order for a state transition on a rollup to be signed off, it needs to be signed off A, by the centralized sequencer, and B, by a set of enclaves. And that can be your training wheel while we're waiting for SNARKs to have a real-time proving. And then the other aspect is that with liquidity providers, you can kind of simulate and fake the synchronous composability, as I've explained in previous talks. And then the other answer is that we will definitely get real-time proving, and it will come much faster than you expect. There's many, many teams working on it. The progress is exponential. And like recently, for example, Starkware came up with this amazing benchmark where they can do 1.2 million hashes per second on a laptop, on a MacBook. So this is like insane performance, and they're only using the CPUs, by the way. Then that's not even with GPU acceleration. So, real-time proving might be like months, not years. And so this bootstrapping phase where you're faking it might be relatively short. A third counter-argument which is put forward is that if you have shared sequencing, you're going to have these super builders. Very, very big builders that are building blocks for many different rollups at the same time. Now, one argument here is that it won't make a difference to the builder centralization. The reason is that we're already extremely centralized, and these three entities, like I know them personally, and they're sophisticated enough to just scale horizontally as required to support as many rollups as required. And so they kind of have this threshold of sophistication where they can just scale horizontally. Another argument that this doesn't change anything is that Flashbots is working to try and decentralize the builders. And let's assume that they are successful. Well, if they are successful, Suave works just as well in the asynchronous case than it does in the synchronous case. And the reason is that Suave is itself a horizontally scalable technology. And so like these two arguments, these two responses on the left basically are saying that it probably doesn't change anything. But I would argue that asynchronous sequencing and block building is actually net negative. And there's two reasons for that. One is that if you have the asynchronous sequencing and block building, and synchrony is indeed very valuable, what are you creating? You're creating incentives for the asynchronous proposers and sequencers to collude off-chain. And so basically, you're incentivizing the creation of sequencing markets like Espresso, but off-chain. And so you'll end up with a very complicated and convoluted and probably like very centralized sequencing marketplace that will give you the synchrony that the market is demanding. So the market kind of always finds a way to get what it wants. But it will be much more clunky than just doing it with shared sequencing to start with. And then there's an argument which I think is even more powerful, is that if you have asynchronous sequencing, you might actually centralize the validator set itself. And the reason is that there's this very simple observation, which is that the bigger you are as a staker on rollup A, and the bigger you are as a staker on rollup B, the bigger the probability that you're going to simultaneously be a sequencer on rollup A and B at the same time. And if you are the sequencer on rollup A and B at the same time, then you can provide synchronous services and extract the premium of synchrony. And if this premium is very high, then there's going to be a very high incentive to basically centralize the validator set so that you maximize the number of times that you're simultaneously a sequencer on A and a sequencer on B. Okay, so that's the end of my talk. I guess L2s have to choose very wisely. Do they want to go down the synchronous path or the asynchronous path? Thank you. Five minutes for questions. Question there. Do we have another microphone?
Thank you. So a very cool presentation. I like your arguments, especially when it comes to UX. But there is one thing I'm not fully getting, because you mentioned something like a shared liquidity between the rollups for DEXs and for lending.
Yeah.
But the way I understand shared sequencing, it will give us atomic transactions, where you can swap on one rollup and on the other rollup and make it atomic. But how is it related with using liquidity or reusing liquidity from the pools between rollups? For that, we also need bridging. We need much more mechanism than just shared sequencing.
Right. So, like, people get sometimes confused between synchrony and atomicity, and this is part of the reason why I define synchrony. Atomicity, as you said, is like atomos. Like, it's like you can't break it. It happens in one chunk. Now, in some sense, like the atomicity is not something that shared sequencing gives you. This is a safety property that things like ag layer gives you. So what you need in order to get the shared liquidity is two pillars. Number one is you need the shared sequencing, but as you said, number two is you need the instant withdrawals and passing of assets from chain A to chain B, and that's the real-time proving aspect. Okay, so once you have real-time proving, you can have real-time settlement, and kind of at a transaction by transaction level, you can pass funds from chain to chain, just like on L1 today, you can pass funds from contract to contract. So the L1 today on Ethereum has a shared sequencer, right? It is the validators, and it also has like real-time settlement. Like every transaction kind of settles in real time through consensus. Any other questions? I guess I have prepared like more counter arguments. There's plenty of counter arguments that people come forward. People say, for example, the web is asynchronous, and so we should be able to build everything asynchronously. And yes, that is true, but like if we have the option to do it like better and simpler, like surely we should do it. And if we don't, then this is an opportunity for a competitor like Solana to just grab a free lunch. And the other thing I'd argue is that like the web is not very well designed, it's not primed for synchrony, and the reason is that it doesn't have shared sequencing, right? You have the Google sequencer and you have the Amazon sequencer, and like those don't trust each other, and so you don't have opportunities for shared sequencing. And then another kind of very common counter-argument to shared sequencing is that it's incentive misaligned. Like I, as a roll-up, I don't have an incentive to opt into a shared sequencer because I lose the fees. And I think part of the problem here is the naming of sequencing fees. Sequencing fees as a name should just disappear because it's a misnomer. The fees don't go to the sequencer, they go to the rollup. So I would call them congestion fees instead of sequencing fees. But it looks like I'm out of time. Thanks again.